We're going to take a look at the concept of a higher order derivative. The idea behind this is that every time we go through our differentiation rules, we essentially come up with another function. So for example, if we looked at f of x is equal to x cubed minus 2x squared plus 2, and we take its derivative, f prime of x will end up being 3x squared minus a 4x. Now, that quadratic function is, in fact, a function. This function exists. It's going to have tangent lines that can be drawn at any point along its curve. So that means that this quadratic can also have a derivative taken. We can take the derivative of that first derivative. When we apply the power rule again, we're going to end up with a function that looks like 6x minus a 4, or a linear function. So the idea behind higher order derivatives is that we're allowed to continue to apply these derivative rules over and over and over again for as many times as needed to come up with more and more derivatives of the original function. The very first function we have here is f of x. F prime of x is considered its first derivative. When we use a double tick mark in there, it stands for f double prime of x, and it represents our second derivative. All of the derivatives do come from the original f of x function, and if f of x changes, it's very possible that f prime and f double prime and all the other derivatives may change as well. Here's some of the notation we're going to see for some higher order derivatives. For various functions, depending on the situation, you may have a y equals equation. You may have a function notation like f of x. Again, you may also have y equals, in which the first derivative is represented by dy over dx. Or if we have a function like f of x and they use the indicator or the operator of d over dx to tell you to take the derivative, that might be another symbol you might see for taking the first derivative. For the second derivative, we use a lot of double primes for the first two columns. But if you're going to use that d over dx type of notation, we could have d squared y over dx squared, or the d squared over dx squared followed by the original function. And that would just indicate for us that we are taking a second derivative. We have to take two derivatives from the original function. The same thing happens with the cube for a third derivative. And when we get to the fourth derivative, we stop using the prime notation and we use an exponent with a little 4 in parentheses to indicate that we are trying to take a fourth derivative. For the notation that was coming from the primes, the pattern of the primes in here, you do want to include those parentheses because that distinguishes between just y to the fourth power and the fact that we're trying to take the fourth derivative of y. So let's take a look at a few examples of using this notation and taking the derivative multiple times. Here we have f of x is equal to our function. Sign is unfortunately in there twice, and that's not supposed to be. And we want to find the first 5 derivatives. So we already have our function, so we're going to find our first derivative, f prime of x, and we're going to apply all the different power rules and the trig rules as needed. There is our first derivative. Now to find our second derivative, we are going to go through and take our first derivative and apply the power rule and the trig rules one more time. There is your second derivative. Now for our third derivative, we're going to use our second derivative that we just had, and once again, apply all the different rules that we know. There's our third derivative. Our fourth derivative, we're going to apply all the same derivative rules, but to our third derivative. And last, we're going to take the fifth derivative which again, we're just going to continue to apply all the same rules. And there we have the first 5 derivatives of f of x. Now notice what happened with some of the terms. We were applying a lot of the power rules to these different terms. For the first 2 terms in our function, they are polynomial terms. And because we're taking 5 derivatives, think about what happened to all of those terms. The 5x to the fourth turned into an x to the third, then an x squared, then an x, then a constant, and then changed to 0 for our 5th derivative. The x squared, the negative 6x squared, changed into an x to the first term, then into a constant, and then disappeared altogether. So if we're taking multiple derivatives, the powers, your polynomials that are in here, may end up going down to 0 depending on how many derivatives you're taking. So if we take a look at example 2, this illustrates this very, very well. We're going to find the 5th derivative of y in terms of x, given that y is a cubic function. So take a moment to find the first 5 derivatives and see what happens. As you can see, all we did was get to the 4th derivative, and we were already at all terms equaling 0. Any derivative thereafter would also only be equal to 0. So when it comes to polynomial functions, any exponents that are, or any powers that are less than the number of derivatives you're taking, those terms will eventually go to 0. If we look back up to our first example, the trig functions will be cyclical. We started off our original function with a sine of x. And because we're not using a chain rule here, we can kind of be very predictable about what will happen. It goes into patterns. It will change from sine to a positive cosine, to a negative sine, to a negative cosine, and back to a positive sine again. So from our first function to our 4th derivative, we've gone through the complete cycle of all the various trig functions between positive and negative sines and cosines. When it comes to our rational functions, or our powers that have negative exponents, those types of terms will still be around the more and more derivatives you take, because we're subtracting 1 from those exponents. We're going to continue to subtract 1. We're going to continue to have more rational functions. So they will not necessarily disappear as we're taking our derivatives. So take a look and take some time to look at example 3 and example 4. In example 3, we're trying to take the 58th derivative in terms of x. And for example 4, we're trying to take the 447th derivative of sine of x. See if you can reason your way as to what this has to be without actually calculating all of those individual derivatives. For example 3, since we are taking the 58th derivative and we're working with a polynomial function, for any term that has a power of 57 or less will become a 0 based on the number of derivatives we're taking. If we did have x to the 58th, we would need to calculate what new coefficient would still be around. But in this case, if you look at all of the various powers in f of x, the highest exponent we have is a 57. So therefore, all of those terms will eventually reach a 0 as all these derivatives are being taken. So we can say that the 58th derivative of f with respect to x will be 0. Now, when it comes to the trig function sine of x, we know that it always follows the same pattern. The derivative of sine will be cosine, derivative of cosine is negative sine becomes negative cosine, and negative cosine becomes positive sine again. So that means this has a pattern that every 4 derivatives, we repeat the trig function that we have. So we can use this to our advantage by knowing that we are taking a 447th derivative by dividing that into groups of 4. By taking the 447 and dividing it by 4, we come up with 111 different times we will go through that cycle. So we will go through all of these 4 derivatives 111 times. What's left over is going to be our remainder. We have a remainder of 3/4 or a remainder of 0.75, or you can look at it as a whole number remainder of 3, meaning we're going to go through 3 more derivatives before we're able to repeat the cycle again. So we go through the process of all 4 of these 111 times, and then we have 3 left over. So we have 1, 2, and then 3 as our last derivative that's going to be our last derivative result. So we can say that the 447th derivative of sine of x will be a negative cosine of x.